welcome to the second lecture on sustainable energy technology. So in the previous class, we discussed various types of energy: electrical energy, electromagnetic energy, mechanical energy, thermal energy, etc. And we saw certain illustrative examples of how such energies come into our day-to-day world. So today we will go over briefly on how to quantify energy using different units of energy that are commonly found in various technical and scientific literature, and then go on to look into the role that energy plays in society today. So in the first slide in front of you, you have the units of energy. Now the SI unit of energy is joule. So joule is basically force into displacement, the standard unit of energy as defined by Newton in classical mechanics. It's the work done by 1 Newton of force which acts over a distance of 1 meter. Alright. If you think of it in terms of power, 1 unit also is watts per second, watt second, because watt is joules per second, the rate of production or consumption of energy. So that is the SI, or the standard unit of energy. Another common unit of energy that you may have heard of is ergs, which is the CGS unit. This is work done by 1 dyne force acting through 1 centimeter. Nowadays, ergs, you will not hear of erg as a unit of energy significantly anytime during this course at all. The unit calorie is a traditional British unit of energy when heat energy is typically considered. Of course, thermal energy is only a kind of energy, but typically heat energy is used, calorie is used when we discuss thermal energy, or say energy content in food products, etc. So you may have heard of this many calories are coming from a certain food intake, or exercise helps us to expend this many calories of energy. Alright. So calorie is defined as the thermal energy or the heat needed to raise 1 gram of water by 1 degree centigrade. So the temperature of water is increased by 1 degree centigrade, the mass of water is 1 gram, and the total energy required to do that process is calorie. A similar energy used for the British unit, the FPS units, foot pound second unit, is BTU, the British thermal unit. It was a very common unit of energy when we talked about coal. Okay. So this is the heat needed to raise 1 pound of water, the mass of 1 pound of water, by 1 degree Fahrenheit temperature. Then we look at a very common unit of energy when it comes to power plants, power production, which is kilowatt hour. So this is the energy of 1 kilowatt of power flowing for 1 hour. Okay. So suppose you have an electrical power station which is generating energy at the rate of 1 kilowatt. Remember, 1 watt is joules per second. So 1 kilowatt is 1000 joules per second. So in 1 second, that power plant is producing 1000 joules of energy in terms of electricity usually. So now, how much energy will this power plant produce in 1 hour? It's 1000 joules into 60 seconds into 60 minutes. Because 1 hour has 60 seconds, 1 minute has 60, 1 minute has 60 seconds, and then 1 hour has 60 minutes. So 1000 into 60 into 60. So that is the total energy produced by this power plant in 1 hour. Correct? So this unit of energy is called kilowatt hour. So 1 kilowatt hour is equals to 1000 into 60 into 60 joules. Basically, that's it. Similarly, 1 megawatt hour will be 10 to the power 6 watts, because 1 watt is 1 megawatt is 10 to the power 6 watts into 60 into 60. So in terms of joules. So kilowatt hours and megawatt hours are larger units of energy, very commonly used in power plant systems. Then you have large thermal units of energy. For example, 1 quad, which is 1 quadrillion, which is 10 to the power 15 British thermal units. So 10 to the power 15 BTUs is 1 quad. So again, a very common unit for when looking at large units of energy when you come to coal, oil, etc. A somewhat smaller unit of energy is therm, which is 100,000 BTUs. So 10 to the power 5 British thermal units. So 1 BTU is the heat needed to raise 1 pound of water by 1 degree Fahrenheit. 1 therm is 100,000 BTUs. 1 quad is 10 to the power 15 BTUs. All English units, all usually used in English in UK and in some parts of the world to denote thermal energy contained in coal, oil, etc. Now, when we discussing oil, a very common unit of energy that has been used for a very long time, and is you will also find a lot of time, not in a lot of places in the technical literature, when it comes to say oil industry, coal industry, etc., is tons of oil equivalent. Capital TOE, ton of oil equivalent. Okay. This is the energy released by burning 1000 kgs of crude oil. So the energy that you get by burning 1000 kg of crude oil is defined as 1 ton of oil equivalent, because 1 ton is 1000 kgs. Of course, in reality, crude oil does not have a constant amount of energy. Different batches will have different energies. So this has been standardized using some standard petroleum blend, and so 1 ton of oil equivalent is approximately 41.868 gigajoules. Giga is 10 to the power 9. So 41.868 into 10 to the power 9 joules, which again converts to 11.65 megawatt hour. Okay, so 1 ton of oil equivalent is around 41.868 gigajoules, which is equals to 11.65 megawatt hour. So why are we discussing so many types of energies? Because if you are trying to compare the energy consumed or energy produced from different sources, some sources will use quads, some will use BTUs, some will use megawatt hours or gigawatt hours, some will use tons of oil equivalent. And you want to collate all that information and compare them to do some of your work in future, say, in energy studies. So you need to know the units and what their conversion factors are so that you can compare them properly. A lot of mistakes happen when these comparisons are not done properly. Alright. So here also, when you look at SI units, there are certain prefixes that come when we look at 10 to the power x. Okay, x can be positive when you are looking at fractional values, and can be negative when you are looking at fractional values, and can be positive when you are looking at large values. Okay. So for example, kilo is a prefix for 10 to the power plus 3. So 1000 grams is 1 kilogram. Very simple. 1000 watts is 1 kilowatts. If you go the next set, 10 to the power 6, so 1 million, typically it's called mega. So 10 to the power 6, 1 megawatt. Okay. Similarly, a megagram is often used, though usually it's less often used. But anything 10 to the power 6 times is mega. Then 10 to the power 9 is giga. So this gigajoule here, it is 10 to the power 9. Then 10 to the power 12 is tera. So 10 to the power 12 of something is tera. There are many other units after this as well, and when you can just look it up in the internet. And if you look at smaller units, then millimeter, for example, 10 to the power minus 3 meters. Micrometer is 10 to the power minus 6 meters. Nanometer is 10 to the power minus 9 meters. and pico 10 to the power minus 12 meters. Alright. So these are kind of common prefixes that you will often find in many places. So after 12, you will also have tera. So this is 10 to the power 12 tera. Then 10 to the power 15 is peta. Okay, I will not discuss those things. And 10 to the power 18 is exa. So other units are also, abbreviations are also present above and below these values. So here is a table from the book that, from the textbook I sourced in the first slide, we said as a recommended textbook. From there I have extracted this table of the energy conversion factors for the various units. Just before that, I also forgot to explain these three units of energy. Electron volt. So this is the energy gain of an electron which is moving through 1 volt of potential difference. Okay. So electron volt is a very common unit in, say, physics and semiconductor industry, where you are looking maybe at atomic scale energy changes. So it's the energy gained by an electron when it moves through 1 volt of potential difference. In battery industries, electron volt is a very common unit, okay, where the units are in electron volts. It's a reasonably small unit of energy. Then another common unit of energy in explosive industries is megaton, MT. So when energy released by 1,000,000 tons, when 1,000,000 tons of TNT explodes, remember 1 ton, okay, is 10 to the power 6 grams, okay, so 1000 kgs, and 1,000,000 tons is 10 to the power 6 tons. So 10 to the power 6 into 1000 kg, so 10 to the power 9 kgs. Alright. So 1,000,000 ton is 1 giga kilogram, 1 teragram basically. Alright. So the energy that is released by that is megaton. Then you also have foot pound, the typical unit in an FPS system, work done by 1 pound of force acting through 1 feet. So these are some of the energy conversion units. So let's look all of these in terms of joules. Alright. So this is electron volt. So 1 electron volt is 1.6 into 10 to the power minus 19 joules. So it's a very small unit of energy. Another common unit of energy, as we discussed, is calorie for thermal energy, energy contained in food, etc. So that is around 4.18 joules. So very close to 4 times that of 1 joule approximately. 1 arg is 10 to the power minus 7 joules. So a small, significantly smaller unit of energy. 1 BTU is 1055 joules. So more than 1 kilojoule, slightly more than 1 kilojoule. So this is a comma and not a full stop. Just remember that. 1 kilowatt hour is 3.6 into 10 to the power 6 joules. So 3.6 gigajoules. Alright, 1 kilowatt hour. Then 1 therm is 1 into the power 8 joules. Tons of TNT is 4 into the power 9 joules. 1 quad is a very big unit, 10 to the power 18 joules. Another unit common in the gas industry is standard cubic feet of natural gas. The energy contained in 1 standard cubic feet of natural gas. And this is 1.07 into 10 to the power 6 joules. Alright. Similarly, you can find all the other units as well here. And this conversion factor might be very useful to you when you are looking at various types of energy and converting one from the other. Now, along with this, there are certain other units that you will also have to do when you are doing your problems or your calculations. Units of area, density, energy flux in watt per meter square, force in terms of newtons, heat transfer coefficient, length, mass, power or heat rate. Another interesting unit here is 1 horsepower, a very old unit of power for especially cars and automobiles, which is around 746 watts. Then refrigeration systems is often expressed in terms of tonnage. So you have a 1 ton AC, okay, or a 2 ton refrigeration fridge, okay. So the tonnage is also an energy capacity, which is approximately 3514 watts. All right, so it's a power it's basically another unit of the power capacity of your electrical instrument. It's 3514 watts, okay. So when you are talking about refrigeration systems, this tonnage becomes a very important unit that you will have to be keeping in mind. Then specific heat capacity, we discussed what's the value, thermal conductivity, velocities, volumes, volumetric flow rates. So these are all useful units to keep as a reference as you go along with your course. Whenever you find some unfamiliar unit, more likely than not you will find this in one of these tables here. Alright. So if you look next up, how do we kind of get a sense of what these various units are? What is 1 joule really? What is 1 kilojoule really? And what is 1 megajoule really? We can quantify them, but can we get a feel of what they are? So here is kind of a fun way to understand this. I'm calling it a scale of energy. I also got it from another book where it was given. So what is the energy required by your heart as you pumps blood throughout your body? It's around 1.5 watts. So your heart, as it pumps blood throughout your body, is expending 1.5 joules per second of energy. So that its power expended is 1.5 watts. Your household light bulb, a typical reasonable bulb, nowadays of course you have better bulbs which are more energy efficient, etc., etc. Typical values is around 100 watts. Okay. So a household old style wire kind of light bulb will expend around 100 watts of energy. Now if you are working hard, for example you are playing cricket, playing football, transferring heavy weight, then you as a typical human being will be expending around 0.1 kilowatt of energy of power. So that means 0.1 kilowatts is 100 watts, correct? And 100 watt means 100 joules per second. So you will be expending 100 joules in 1 second as you do reasonably hard work, running, jogging, playing, moving objects, heavy objects, etc. So that kind of gives you a feel of how much energy you are expending and how that tracks with the units that we are familiar with. You are expending 100 joules as you run in a track, for example. Alright, per second of your expenditure. So if you run for say 1 hour, then it's 100 into 60 joules. That is how much? 1 minute, then you 100 into 60 joules you have spent. And again, if you run for another hour, 100 into 60 joules. Alright, so that's the energy you have lost in that 1 hour of hard work. Okay. So these are very typical kind of values. Here. So if you now move from a human being to a horse, a draft horse, big heavy horse that can lift carriages, etc. Such horses can work hard and spend around 1 kilowatt of energy per second. So 1 kilowatt power it can expend as it runs, carrying loads, etc. So a horse is can generate 10 times as much power as an average human. So you as a human being can generate 0.1 kilowatts or 100 watts like your light bulb. So the total energy requirement of a human being as it is working etc. is less than 100 watts. So it's a human body is very energy efficient in that sense if you think about it. But a horse can pull more, so it can do the work of 10 human beings. So 0.1 kilowatt to 1 kilowatt is 10 human beings. Then if you think of a portable floor heater, suppose in a cold space you have portable radiating heating systems. So that will expend around 1.5 kilowatts or 1500 watts of power. So now you are looking into your household appliances. Then from your household appliance you are going to your car, a compact Maruti Suzuki kind of an automobile system. That will expend around 100 kilowatts of power as it zooms through the roads. So 100 into 1000, so 10 to the power 5 watts. So a compact automobile, if you look at these two comparisons, can generate the power that 1,000 human beings can generate. So a car is almost equal to 1,000 hardworking humans in the amount of power it can produce in its IC engine systems. An SUV slightly bigger, 160 kilowatts, so it's around 1,600 human beings working hard together. Okay. Or 160 horses. So that's where you have a discussion of 1 horsepower. So people were always comparing electrical and mechanical appliances to horses that were more common in the medieval era before industrialization. So that's where the unit of horsepower came into being. But you can think here that it's 16,000 humans, 10,000 humans. Okay, 1,600 humans, 1,000 humans. So that's what it can do. Now when you look at a combustion turbine, so when I am saying a combustion turbine, which means a typical gas turbine that is there in a small scale power plant or a small scale natural gas power plant. Alright. So that can expend or generate energy depending on whether you are using it to generate electricity or using it to run an aircraft of around 5,000 kilowatts or 5 megawatts. So a typical combustion turbine will expend power or generate power of about 5,000 kilowatts, which is equivalent to 50,000 human beings working simultaneously. Now you go into a large ocean liner, 200,000 kilowatts or 200 megawatts. So this is around 2 million human beings working together. So 200,000 to 10. So 2 million human beings working together will generate the same power as a large ocean liner. Similarly, a big aircraft like Boeing 747 at cruise, not takeoff when it is generating a lot more power, just cruising through air, that will generate 250 megawatts of power, expend 250 megawatts of power. So 2.5 million human beings working together can generate the same power as a single aircraft, Boeing aircraft. So these are all energy expending devices. What about energy generation? So a typical coal power plant is a 1 gigawatt coal power plant. So 1000 megawatts or 10 to the power 6 kilowatts. So clearly a typical coal fired power plant can generate as much energy as 10 million human beings. Okay. So this is 2.5 million human beings. It is consuming, this is generating power at the scale of 10 million human beings. Coal fired power plant, 1 gigawatt of power. And then you have the Niagara Falls hydroelectric power plant. So it's a hydel power plant, runs on water energy. We'll discuss hydel power plants later. 2 gigawatts it can generate power at. So it is approximately then 20 million human beings. So you can see how our modern energy generation and energy consuming devices have energy consumption and generation capacity thousands, hundreds of thousands and millions of times as much as a single human being can generate. And this is the key that undergirds our current industrial civilization. Because we have developed technologies by which we can generate usable energy at such high volumes, and then also technology that can consume such that energy at such high volumes that we can create this kind of sophisticated devices like cars, like trucks, like your power plants, etc., that undergird our industrial civilization. Our civilization rests fundamentally on extremely large energy fluxes that we have harnessed through our technological means. Without that, we cannot have this level of development as we are seeing in the world today. Remember, your computer or your cell phone will consume more energy than you. Okay, and unless we can provide that energy, none of this will work. So their existence and the reason they work, cars, cell phones, computers, aircrafts, rockets, etc., is because we have been able to harness energy at such scales. Okay, so that is one of the fundamental basis of our society today, along with, in the last 20-30 years particularly, the information revolution, that we are able to harness computational capabilities which in sheer quantity, if not in quality yet, are much larger than what a single human being can store or process. All right. So these two together, if you think of history of technology, are the two most important revolutions on which modern society is based on. So this course is about transitioning the first pillar, this energy harnessing ability and energy consumption ability, from a less sustainable basis, which is our fossil fuels, our coal, oil, natural gas, etc., to a more sustainable foundation, which includes renewables and includes many other ways of sustainable power technology, energy technologies. So that transition is what we are discussing. How we can make that transition, what are the gaps that exist, what are the technologies that exist, a deep dive, all right, with a broad overview.